Good morning. In today's session, we will see about magnetic force on a current carrying conductor. If you can recall, in the last few sessions, we have learnt about the force acting on a charge which is moving in a magnetic field. If you take a charge q and moving with velocity v, when it enters the magnetic field, the charge experiences some force, and the magnitude of this force is given by qvb sin theta. If you can recall, we have learnt, like, if we take a charge q moving with velocity v and entering a magnetic field b, experiences a force, and the magnitude of that force is given by qvb sin theta. This is about one charge. Now if we have a conductor, current carrying conductor, so force on a current carrying conductor, if you have a conductor which carries a current I, and if you place that conductor in the magnetic field, what will be the force experienced by the conductor? We can say, like, because all the electrons in this conductor are moving, each electron will be experiencing a force, its own force. So there will be some total magnetic force which will be acting on the conductor. Now today we will see the how this force can be measured. Now let us say a current carrying conductor placed in a magnetic field. Let me draw a magnetic field here. Let us say we have a magnetic field and the intensity of the field is B. So we have a magnetic field B, and let a current carrying conductor is placed in the magnetic field in such a way that the conductor makes some angle with the field. So this is the current carrying conductor. A conductor carries current I and is placed in the magnetic field in such a way that it makes an angle theta with respect to the magnetic field. Let us write these points. Let a current carrying conductor is placed in a magnetic field as shown in the figure. Means the conductor makes an angle theta with the magnetic field. Now let us say the free electrons in the conductor are moving with drift velocity v. So let v is the, or vd, I can take vd as the drift velocity of free electrons in the conductor. Drift speed of free electrons in the conductor. Now when the electrons moves with the drift velocity vd, each electron experiences a force. So the force due to magnetic field the force experienced by each electron due to magnetic field is, as we know the formula, F is, if E is the charge of the electron, then it is E into Vd into B sin theta. So force on each electron, force due to the magnetic field, you can write force due to the magnetic field on each electron is F is equal to QVB. Q you can take it as E because it is an electron. Velocity is Vd and field is B. The angle between the V and B is theta. Now this is the force on one electron. We'll have many free electrons moving this conductor. So now we will see what is the total force experienced by all the electrons in the conductor. For that, let us assume N is the number density of electrons. Let N is the number density of free electrons. Number density means electrons per volume. Number of electrons per volume. Number density. So to find out the total number of electrons, you have to multiply N by its volume. Number density of free electrons. Number density of free electrons in the conductor. Number density of free electrons in the conductor. Now consider a small current element dl. Okay, so consider a small current element dl. Small current element dl. If m is the number density of free electrons in the conductor, then total number of free electrons in the current element dl is, it is dl is N, capital N is equal to NaDl, where A is the area of cross section of the conductor, where A is the cross section area of conductor. So now what we took, we calculated what is the number of electrons in a small current element dl. Now when you take a small current element dl, it has this much electrons, n into a into dl. Now what will be the total force acting on this element? Therefore force due to magnetic field on current element dl of conductor is I can write it as dF equal to number of electrons multiplied by force on each electron. You can write it as dF is equal to number of electrons in element dl multiplied by force on each electron. So therefore dF is equal to F is equal to number of electrons in each element is, so I can write it as n into F, and we have calculated n is n into A into dl, n into A into dl into what is F? It is E into Vd into A B sin theta. Now rewrite this equation. I'll write it as n into E into A into Vd, n E A Vd into dl B sin theta. N A dl into V dV sin theta. So N E A into Vd into dl into B sin theta, and we know this is n into E into A into Vd is equal to I. So this is equal to dF will be equal to I into, because the term which I have written inside this blue bracket is equal to I dl B sin theta. This is in the current element dl. Now net force on length L of current I carrying wire can be written as net force on length L of the current carrying conductor is now this is for dl. So if you are considering length L of the conductor, net force on length L of the current carrying conductor is F is equal to I into, so replace dl by L B sin theta. So the force is actually written as F is BIL sin theta. BIL sin theta. This is the magnitude of the force. F is BIL sin theta. BIL sin theta. Or in vector form you can write it as F as I into L cross B. F is BIL sin theta. And the direction of this force is given by Fleming's left hand rule. You can refer our previous class for Fleming's left hand rule. I will just recall it. You have to stretch the first three fingers of your left hand, that is thumb, forefinger and middle finger, mutually perpendicular to each other, with your forefinger pointing in the direction of the field, middle finger pointing in the direction of current carrying conductor, then thumb will give you the direction of the force. The Fleming's left hand rule we have taken in detail when we did the force experienced by a charge when it enters the magnetic field. So you can refer our previous session for Fleming's left hand rule. Now for the magnitude of current carrying, magnitude of the force experienced by a current carrying conductor is given by F is BIL sin theta.